As the name suggests, this series presents talks on foundational topics. So these are basically lectures on foundational topics rather than research talks. And over the next 3 weeks, Azeem will tell us about p-adic numbers.
Thanks. So the plan is to learn something about this number system, or rather a series of number systems which are called p-adic numbers. So I will come to what they are maybe by the end of this session, hopefully. But before that, like kind of why should we care about these things? And I think like probably the first thing is just curiosity. So they are some kind of alternatives to real numbers. So we understand real numbers, and part of today's lecture is just to try to understand what I mean when we say they are alternatives to real numbers. And so we will spend a lot of time there. So and in mathematics, if we have some construction, it's good to try to understand in how many ways it can be generalized. And in some sense, these are the only alternatives to real numbers, although I will not explain here what I mean precisely when I say they are the only alternatives. Okay, so they are alternatives to real number. So explore to R. And the other thing, so which is the reason I got into this business, which is they are an important handle on finite abelian groups. So if you have taken a course in abstract algebra, you know what finite abelian groups are. You have seen the classification. If you haven't, I will come to it what they are. And the most important, but the important example we should have in mind are integers modulo p. So I can consider integers from 0 to p minus 1, let's say, and I can define addition or multiplication on them by adding or multiplying them as numbers and then taking the mod p. So but all maybe I don't have to take, so where p is a prime, and you should remember this p. So this p is related to the p here, but I can also just say z to the pn. So instead of taking instead of doing addition and multiplication modulo p, I do it modulo p to the n. And the fun thing about p-adic numbers is that they allow me to, in some sense, to treat all n's at once. So instead of working over zp square, z mod p square, z mod p cube, I work over p-adic numbers and treat all of these cases at once. And so and they involve primes, which means number theorists are interested anyway. So this is all they need to hear to be interested in something. It involves primes. So interesting for number theorists. But they are also, I think, like a very nice showcase for the point of view, what at least for me is the point of view of abstract algebra generally, which is that instead of trying to remember things, by naming them, what we should try is to remember them by the properties they have. And somehow if we specify enough properties of an object, we know what the object will be in some sense. So this is kind of, and so this will be kind of, this will be my point of view during the talks. So we want to understand them, these numbers, by what kind of properties they have. So the first thing, if we want to understand what are p-adic numbers, would be the question, what are numbers? And it's probably one of the cases where I don't have a good idea, because although like we are very used to dealing with numbers, we are never given a definition of numbers. And I think the reason is the same. It's kind of like it is the abstract algebra perspective that what we mean by different things we call numbers depend on the setting we are in. Properties of natural numbers are different from properties of integers, which are different from real numbers, and there is not much that joins them. So we can formalize different number of property. We can formalize different properties, but we give those structures different names. None of them are called numbers anymore. So we will talk about groups, rings, fields, integral domains, etc., etc. But we will come to them when we need them. So I don't know. So let's just talk about some examples. So the simplest thing is are natural numbers, right? And I always forget whether they are supposed to have 0 or not, but for me they have 0. So natural numbers, and they are very easy to define, right? So there is a number. It doesn't matter what I call them, but I write it as this circle, and then there is a next number, and I write it as a line, and there is a number after it, and I write it as a 2-line. Number after it, I write it as a 2-line, and no matter which number I have, I can always create the number next to it, and the way is I just add another line. So this is an inductive definition of natural numbers. So and so on. So this is, so no matter what number you give me, I am able to give you a number which is next to it. So this is the definition, and the next thing we want to know is what kind of thing I can do with these numbers. And the simplest thing is I can just define this operation, which I call addition, which goes from, so let's say natural numbers n. So I have a function from a pair of natural numbers to natural numbers, and it goes like this. So if I want to add 0 with anything, it's just x, and or x plus 0 is also x. So the question is, what do I do with when both the numbers have some lines in them, right? So in that case, it's also very simple. Plus, what I have to do is just erase this symbol. So I get a bunch of lines. This bunch of lines represents some natural number, and that's the addition of these numbers, right? So very, very simple. And similarly, I can also define another binary operation, which I call, so multiplication, and that I can also define inductively. So what I want to do is I want to, again, in this case, what I want to say is 1 times anything is 1, 0 times anything is 0. And so the question is 1, oh yes, thanks. And maybe I should have written them in the opposite order. I will write them in the opposite order now. Okay. So here, and 1 times x is x. And so what happens when I have this times x? So what I will do is I will just remove one line from here and write x plus the other line multiplied with x. If I wanted to do 3 times x, what I will do is again remove one line, write x plus 2 times x. So I can continue like this, and I get a definition for multiplication. Okay, fine. So this is here. It's not really even its own thing. It's just defined in terms of this other operation I did. So one thing I am actually interested in, but I didn't write there, is solving some kind of equations. So mostly it will be polynomial equations. We will come to this in the next lectures. But so the one thing, so we have these numbers. The interesting questions are what kind of equations we can solve using these natural numbers. And yeah, let me go here instead. But instead of let me talk about what kind. So instead of talking about what equations we can solve, we can definitely solve some, right? Like x plus 2 is equal to this has one solution, and that means x is equal to 1. And there are a bunch of other equations we can solve, and since we can do it, they are not that interesting. Okay, but let me say something else, right? So this is a very simple way of representing natural numbers. Addition is the simplest it can be in this, right? So, but the problem with this is, if I have a very big number, it's going to take me a lot of space to just represent that number. So we don't really use it, right? So the base 10, which hopefully is something everyone knows, the problem that solves is that of space. But it makes the rule for addition a bit more complicated, but not too complicated. We can deal with it. Okay. So what equations can't we solve? And so one thing I can't solve is maybe is this 2 plus x is 0, right? So this has no solution in the list of numbers I have defined here. So what do I do? So it will be kind of first instance of what we will do a lot, which is just try to come up with a bigger set which includes this set, and create this set in such a way that these equations are automatically solved. So in this case, what I can do is maybe I add one more element which I will represent as a line, but this time horizontal, and this. And this just has the property that -1 is 0. So this number plus 1 is 0. So I have just added it by saying I want this equation solved. So I want the equation x plus 1 is equal to 0 solved. So I'm just going to add a solution, right? So this is, but I also want this property. So I want some new set. Let me call this set z. So a new set z. This z includes this -1, but I also want it to be, I should have said something earlier. So what I have is a new set z, and I want to extend my operation z to this set. So z times, so z to z, and multiplication, I would like the multiplication to extend to z plus z to z. And what I can realize pretty easily is that if I just add this, I cannot really have this. I cannot have an operation. The addition cannot go from z times z to z. So I will need to add more numbers. And it's pretty easy to find what those Moore numbers look like. So what I need is, so minus 1 times some number x, and so where x is a natural number, right. So I have some natural number x, minus 1 times x is not really in this set unless this x is 0 or 1. So 1 I have added by myself. So I just write this, I just consider this as a new number. And so I define minus x, this is for me by definition the multiplication of minus 1 times x. And I can check, so I want to extend them, and the way I will extend them is, okay, on this set, this addition and multiplication have some nice properties. So I want them, so what are these nice properties? Maybe I should have written them before, but I will write them here. So this is x plus y is y plus x, and x times y is y times x, and then x times y plus z is x y plus y z, x y plus x z, yes. So this is something that I want to have, and if I start imposing them, what I realize pretty quickly is that I don't really have any freedom. In the sense that, for example, if I have this x minus x plus x has to be 0. Similarly, minus x times 1 has to be minus x, which I get from here, and so on, so on. So we get, so there is an obvious way. If we follow our intuition about addition and multiplication, we basically write them down. So if we know what they are for natural numbers, we get them for integers. So there is not much. We don't really have much of a freedom in doing this. And this is kind of, I guess, will be a general feature, if we try to extend our set by a little, but we still want our operations to be nice, we actually have to often extend it by a lot. So there is some minimum amount of new elements we must add. And in this case, the new elements are 1 for every non-zero element of natural numbers. And so we have, I have this set integers. We have integers, and if you go to base 10, you can write them as like minus 1, minus 2, minus 3, and then like 1, 2, 3, the positive ones and the negative ones. So if I have integers, what I can do is I can solve all equations of the form. So I can fix n, which is an integer, and I can always solve an equation of the form that x plus n is equal to m, right? And the solution will be x is m minus n, and this is again like a shorthand for saying x plus m plus minus n. Okay. So this, so far so good, but what I can't generally solve is an equation of the form n x is m, right. So this is not, I will not be able to solve them. To solve, in special cases I can solve them. So what can happen is that maybe n m is n times a, then x is the only solution. But this will not always happen if we restrict ourselves to integers. And one example is, so there is no solution for 3x 7, right. So, this is a perfectly valid equation with only integers, in fact only natural numbers, and I do not have a solution. So, what I want to do is I want to add. So, I want to further extend the integers so that I have a solution to these kind of equations too. And before I do that, let's, since we are going to see a lot of sets with very similar properties, let's start giving them name, right. So and we already have some examples. So the first thing I will need is group, and actually let me just stick to abelian group, since I won't talk about anything non-abelian today. Group. So it's a set G with an operation plus, and we want all these properties. So plus, and then there's also 0 belongs to G, and there's 0 plus x is x, x plus 0 is x, and what else I need? So x plus y is y plus x, x plus y plus z is same as x plus y plus z. So I don't care in which order I add numbers, I don't care how I bracket if I have more than one additions. And the last thing, so all of this is true for natural numbers. The additional thing we need to get a group is for every x in G, there is a minus x such that x plus minus x is equal to 0. And then if you have taken linear algebra, you see like from some pretty simple manipulations we get that this. So this is called the additive inverse of x, it is unique, this 0 is unique. So there can't be two such, although it's not part of the definition, you can't really have two different minus x's which both satisfy this property. Okay. So this we'll call group, but our integers are a bit more than that because of the addition. And what happens, so in that case, so there is, so ring would be, so again a set R with plus multiplication 0 and 1 and R plus and 0 form a group, and plus, so multiplication again goes from ring to it, and it satisfies that A times 1 is A, and the other thing that I want is again associativity. So A times B dot C is A dot B dot C. And so right now I just have two operations, I connect them by requiring distributivity. Maybe I should not draw this line here. So A times B plus C is AB plus AC. So kind of what the thing that we use to extend the addition. So this is basically everything that we need to extend the addition on natural numbers to that of integers. So we will need, we will see these structures again and again. So right now we have a ring which is called integers, but with this amount of structure we can't solve an equation like this. So we need more, but there. So what we can do is we can try to just add more elements. So there is like kind of a very standard construction for this, and which we can do as follows. So, I define a new set. So, I consider a new set, and the elements of this set are of the form p over q. So, they are just tuples. So, I need two integers, p belongs to z and q belongs to z not equal to 0. So, I consider these tuples, and what I want to do is to extend multiplication and addition to them. So, here it's a bit more involved, but the way it works is this. What I can do is I can say, okay, I have p plus q and then r over s. I will write them as, so this again, so I want to write it in the form of ratio of two integers, and I will just do it qs and ps plus qr. So, this is, I do not know, familiar from 6th or 7th grade. When are we taught this first? Okay. And p over q times r over s is pr over qs. But so this and this thing seems to work well enough, except it's not quite enough for me to solve this equation. So naively, so I know the solution I was taught, and the solution should be something like x is equal to 3 by 7 or 7 by 3, yeah, 7 by 3. And if I look at here, so what I should do is, so, and if it is actually a solution, what I should get is that 3 times 7.3 is equal to 7, right. So, but there is nothing in my rules that allows me to say this. So, what I want, so what I have to do is put down this cancellation condition by hand, because the set of tuples is too big. So, I cut them down by saying that p over q is same as r over s. It basically means that p times s is q times r. So now I can do this manipulation, and now I have solutions to equations. So, now I have all the solutions to the equation of the form I can solve now. So, this set which is the set of tuples of integers with this relation, and addition and multiplication is called natural numbers. No, the rational numbers, sorry. So, defined. So, we have rational numbers q, which is again this set pq and p over q is equal to r over s, ps is equal to qr. So, in this set I can always solve equations of the form, let us say what I had written before. So, m times x is n always. So, for m non-zero always has a solution, for m not equal to 0. If m is equal to 0, I do not know what is there to solve, since x has just disappeared. Okay. So, we have this, and we have arrived somewhere, but again if we can solve these equations there are other ones which we still can't. And I will give examples of 2. Oh, but before that, let me write down the axioms of the algebraic structure we have arrived, which is that of a field. So, field is again like the data I need is the same, some set, 2 operations plus multiplication 0 and 1, and what I want is f plus 0 is a group and f except 0 multiplication and 1 is a group, and again the property that relates addition and multiplication as before, which is distributivity AB plus AC. So the fields will be very important for us, because the p-adic numbers we will see will form a field. And again, so in this field, which is kind of the first one we have seen, we can solve some equations, but not a lot. So I will. So there are 2 examples of the equations which we can't solve here, and I want to focus on some ways, in some sense in which they are pretty similar, and in some sense in which they are different. And so the equations are x square is 2 and x square is minus 1. Right. So the first one, so to see that I can't solve the first one, I need to learn about prime factorization. But there is an argument which says that you cannot find a number p over q such that its square is 2, and we do it by basically matching prime factors. So I will not go through this argument, but it's pretty simple, and so we can't solve it. And this one is maybe very easy to see we can't solve, because x square for any rational turns out to be positive. So there is some ordering principle which tells us that this equation can't be solved. So now there is a fork in the road about how you try to go about solving these. So how do you want to enlarge rational numbers to solve these equations? So if you are maybe mostly an algebraist, drunk on these kind of constructions, you said, okay, no problem, I will just add more elements to my field. So what I will do is I define a field, so which I name as q square root of 2, and it consists of the elements of the form a plus square root of 2b. So this is a rational number, this is a rational number, and this guy I have added into my field, and this is defined by, so this is just a new symbol, and the only meaning it has for me is that if I square it, I get 2. Right. So now I have the solution to this equation, and I have it because I added it by hand, which is square root of 2. Similarly, I can do the same thing with this. So, but in this equation I still don't have any solution for x square. In this field I don't have any solution for x square equal to minus 1. I can also define another field, and here I do the same thing. It's a plus square root of minus 1 times b. A and b are rational numbers, and this is just a symbol which stands for something whose square is minus 1. So again I can solve, I can solve this equation, but not this. If I want to solve both, what I can do is I can just add, instead of adding one element, I can add 2. So square root of 2 square root of minus 1, and this will be the numbers of the form C, where A, B, C are rational numbers. So, this lets me solve more equations. I have a bigger field, and in this case, right, like there is absolutely, in this perspective, there is absolutely no difference between whether I want to solve x square is equal to 2 or x square is equal to minus 1. The way out of the predicament is exactly the same, just add what you want. But in this field, you cannot have square root of 3 still. So, maybe you can add that. But if so, this is kind of like algebraist is pretty happy. We are making a bigger field which can solve the equations we want. But if you talk to a geometer, he might not be so happy. So because him, the lack of the solutions for these two things does not look the same. There is a difference between them. Because geometer somehow knows that there is, so I have these rational numbers, and on rational numbers there is some divinely ordained distance. So there is some divinely ordained distance, which means so there is a function d. It takes in two rational numbers x, y, and it gives me, it tells me how far the two numbers are. So it's we can write it in terms of another function which we call the norm or absolute value, and its absolute value of x minus y, and this function itself is just x bigger than 0, x less than 0, minus x, yes. So there is this distance, and he says that you can realize that these two equations are very different if you try to figure out how far from a solution we are. So what you say is okay, so what is the minimum value for x square plus 1. So it's like, okay, how close can I get to 0 here? And the answer is the minimum value is 1. So x is equal to 0. So I am somehow pretty far from finding a solution. It's not like I cannot get too close to finding a solution, but what is value for x square minus 2. So what is the distance, what is the minimum distance I can come from solving this equation? And here it's okay, not as easy as finding this, but let's try. So one thing I can do is try x is equal to 1, and what I will get is that 1 square minus 2 is 1. So let's call it like d min. So what I know is d min is less than 1. So now I can try to do an algorithm which is not very smart, but it will at least let me test how close I can get to this. So what I can do is I can try, so what I see is that 1 square is 1 which is less than 2. So I will try increasing this number slightly, and so 1 square, 1.1 square still less than 2, 1.2 square still less than 2, 1.3 square is less than 2, 1.4 square is less than 2, but 1.5 square is actually bigger than 2. So I stop here, I pick 1.4. So I pick 1.4, and 1.4 square is I think 1.96. yeah, okay, 1.4 square is 1.96. So, d min is less than 0.04. But I don't, so I know I can maybe able to do better by checking some numbers between 1.4 and 1.5. So, I check, I think 1.41 is still less. I think 1.42 or which one is, which one do I stop?
1.41 is less.
Yeah, and 1.42 is still less.
More. No, yeah, I think it's more.
Is more?
Because the square root is 1.41 something.
Okay, it's 1.41. So 1.41 is less than 2, and the distance is less than this one. So somehow by increasing, so what I can do is I can always stop before reaching 2 and keep increasing the number of digits. And this is not a very smart algorithm. We can do like all this much more quickly, but it at least works. And what it tells us that if I keep doing this, if I keep adding more and more digits like this, I can just keep making this d min smaller and smaller. So somehow, unlike this case where I knew there was a minimum distance, I cannot come too close to a solution. Here it seems like I can come as close as I want to a solution. So the geometer says this algebraic nonsense, it works in its way, but it's not very helpful for me, because for me the problem is not so much that I don't have this solution. That might be like a problem for number theorists who cares too much about prime factorization. But for me, I want to measure things, and the problem is that I can come as close as I want to a solution, but still not have a solution. So I do not want to solve this imaginary problem maybe where I just keep adding anything I want. I want to solve this problem that I want to have. So if I can come arbitrarily close to a solution, I actually want to have a solution. So this is done in terms of these sequences, so these functions which are called Cauchy sequences. So let me talk a bit about what both of those words mean. So sequence, so let me first define this word sequence. So sequence is a function S and its domain is natural numbers to, let's say for us it will be for most of the time a rational number. So it's just a function, and I can represent such a function by, okay, first I will tell you what the value of this function at 0 is, what the value of this function at 1 is, what the value of this function at 2 is, and so on. So if I tell you what the value of this function at any integers n, and I do this for all the, no, not integer, natural numbers, and I do this for all the natural numbers, I have told you what the function is. So I will represent this function as a list where the first element is the value at 0, second is value at n, 1, third is value at 2, and so on. So let's see what's happening in here. So what we have a sequence of rational numbers such that they are very close to each other, and they are becoming, so because I am always adding only the last digit, I am only changing the last digit, as the sequence progresses they are also becoming closer and closer to each other. So this is kind of the intuition behind Cauchy sequences, and maybe not the easiest thing to formalize if you try to do it without thinking, right. So this is nice thing about algebra, you almost don't have to think. Here you might need to think a bit more. So it is a nice thing.
You made it
No, but this is again, having to think less means you can think about more interesting things maybe. This is like, if it needs less brain power, let's aim higher, right? So it's like, okay, so we have a, so we can have like, but before that, let me, before coming to Cauchy sequences, let's like, okay, there is some structure there, and because these are functions and these are functions and the codomain, I know how to add elements of codomain. So what I can do is I can define addition and multiplication on the sequences. So S plus T n, so the value of S plus T at n is just S of n plus T of n, and this is S n times T n, and because this is this associative commutative, oh no, why, oh, okay, my writing is deceiving me a bit, this is not plus, okay. So since both these addition and multiplication are associative commutative and addition distributes over, no, multiplication distributes over addition, we see that we will get the structure of a ring, right? And there is a 0 sequence, so the 0 sequence is just 0 0 0. There is a 1 sequence which is just 1 1 1. So these already give us a ring. Dividing, which is like, so which is just taking pairs with that relation, is a bit harder because of that 0 thing. So if there is 0 somewhere in the sequence, then I might be in the trouble, so I will not do it now. At some point we will have to deal with this fact that we don't have a division, right? So we have a sequence, and so we have sequences, but there are a lot of sequences. Some special kind are the ones like this, so that the elements of these sequences come closer and closer to each other. But again, this is something that needs to be formalized a bit carefully. So Cauchy sequence is a sequence S such that for every epsilon bigger than 0, and the bigger than 0 is this is because this epsilon will be some distance, there is an n in natural numbers. So my domain such that if I have any two natural numbers mn and mn are both bigger than this n, then the distance of Sn minus Tn will be less than epsilon, or Sn Tn, yes, or maybe because I will keep forgetting this, I will just write it in terms of the absolute value Sn minus and Sn and Sm. I don't know what this T thing is. So the distance between these two elements will be less than epsilon. So so what this says is, no matter how close, so they are very close together, and no matter which distance you pick, if you start your sequence, if you go very far into your sequence, all the rest of the elements will fit inside this much length, right? So this is what it's saying. I can, if the elements which are far away, I can fit them into as small, I can fit all of them into as small an interval as I want if I go far enough. And so again we have this ring, and then there is this restriction. And the nice thing about oh, so the nice thing here is this restriction plays nicely with this addition and multiplication. So, if ST are Cauchy, then S plus T is also Cauchy. And the only thing we need to do this is to use the property of absolute value, which is that absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. So, if we keep this in mind, we will be easily able to find such epsilon if we know similar things for S and T. And similarly, if S T are Cauchy, and this computation is exactly the same. If you like in calculus, we do that limit of A plus B is equal to limit of A plus limit of B if those two limits exist. So, in this case, it's more or less the same computation. If Cauchy, then ST is Cauchy, and here I will, in addition to this and the result, I will also need that absolute value of AB is absolute value of A times absolute value of B. So we have this. So, what we know because of this, and you can see like these two sequences are Cauchy. So, here it is very simple because the distance between any two elements is just 0. So Cauchy sequences actually form a subring of the ring of these sequences. So, they have some nice structure, but this is not the structure I want, right. So, I do want a field, I want a ring, and in fact, I want a field which contains rational numbers, but allows me to solve some more equations which are equations like x square is equal to 2. But the Cauchy sequences form a ring, but it is not this ring which allows me to do that, because remember what I am interested here is not the sequence itself. The sequence is just a means to an end. What I am interested in is somehow the end of this sequence. And so, what do I mean by that? Because again, the end is not, there is no rational number which ends it. So, and x. So what exactly do I mean? So, again, so we use something which is again close to what we do in calculus, which is we define the limit of a sequence. And what we say that limit of a sequence is, let us say, L if for every epsilon bigger than 0, there is an n such that if small n is bigger than n, then the distance between Sn and L, so the limit is less than epsilon. And another way of kind of phrasing this fact that we do not have a solution for x square is equal to 2 is saying that the sequence that we were constructing by adding more and more digits and getting closer and closer to square root of 2, that does not have a limit in rational numbers, right. So, and this is something that we know because of prime factorization. And so we don't have any, so we do not have, so often the limit does not exist, and this is true in rational numbers. So, and this is the problem we basically want to remedy. So, one way of doing that is, okay, again I want a bigger set. So, I will take this set to be set of the sequences, but just like rational numbers, this set is too big. I do not care about the sequence is just a means for getting to the limit. So, I will identify any two sequence. So, I will identify any two sequences which have the same limit, right. But again, this saying they have the same limit needs to be clarified. What does it mean? They do not have a limit in rational numbers. So, what do I mean when I say they have the same limit? And so, what I care about is not so much whether the limit exists or not, is whether what's the distance between their limits, and that I can define even I stick to the rational numbers. So, I define this new set. So, let us call it like R. Cauchy sequences but I have a relation which is, so a Cauchy sequence S is same as a Cauchy sequence T if limit of absolute value of S minus T is 0. And this makes sense. This equation makes complete sense staying within the rational numbers. I am just saying take two sequences, their differences in other sequences, and although they may not have limit, their difference might. And if the difference is 0, I will say that they are the same sequence. I do not care, for me they are the same. I have reached the same endpoint in some sense. So I have, and I can check that even with this identification, I still have nice addition and multiplication. And this follows again from the fact that if the limits play nicely with addition and multiplication. Okay, so I have this set which is the set of these new numbers, which is a set of which I will call the set of real numbers, and I actually want to be sure that I can now solve that equation, that I have a solution for x square is equal to 2, right. So, but again, so one thing I need to clarify here is what do I mean by this equation, right, because 2 is not a sequence. And so this is a question in much sense I have extended the set of rational numbers, because set of rational numbers does not consist of sequences, but it's very easy to give a sequence just like this. If I want to put any rational number inside my set of sequences. So, if let us say R is a rational number, then in R I can represent it with the sequence all of whose elements are R. So, I only have, so my only sequence, so my only element is R, and it is definitely Cauchy because.
And you can also represent it by any sequence whose any number of
finite elements are different.
Are not R,
yeah.
but after that is R.
Yes. Yeah. So, we will always have like a lot of representatives for the same sequence, but this is kind of the simplest, so it does the job. Okay.
That's covered by the similarity.
Yeah. So okay, so we have so I want to find the solution to x square is equal to 2, and it's almost kind of the algorithm we had before, right? So what we had was just saying, so we have a sequence such that if I take the square of the elements in that sequence, the distance between 2 and them decreases and decreases. So that sequence and the distance between them in the limit is actually 0, which is just saying that sequence, so if I have that sequence whose first few elements are 1, 1.4, 1.41, so S, and I keep finding more and more elements of the sequence using the brain dead algorithm I described. So I can take S square, and I have a sequence which represents 2, which is 2, which consists of only 2's. If I take the limit of this sequence, I will get 0. And this is exactly what we meant when we said that we can get as close to the solution of S square is equal to 2 as we wanted. So we have a construction which works pretty generally and plays nicely with distances, right? So the question that will get us to p-adics is how much can we play with this construction? And again, so if maybe if you're a geometer, we say like you shouldn't play with it, that distance is God given, accept it, but maybe the number theorist will reappear and say, but I want to play with it because maybe I can define some other distance which lets me do some number theory. So again, so distance is not the only thing we have to play with here, but if you follow this construction, what you will notice is that once I have defined the distance, this addition and multiplication I don't really have much choice. There is a natural way. Maybe if you are very smart, there is some way to play with it. I do not know, but the distance is a much more manageable object than playing with addition and multiplication of sequences, and maybe we should at least start there. So the question is, can I come up with some alternate distances? And again, so there the question would be, what do I mean by distance, right? So I had this function, I said I will call it distance, but if I want to generalize it, I should have some understanding of what properties I want, and the properties that I want are the ones that allow me to carry through this construction. And this construction is called completion. So this is in some sense. In some sense, what we want to do is what are other possible completions of rational numbers. So we have rational numbers. We have a nice field. Oh, and actually, I did not say something about why R is a field. Let me come back to that. So what we will talk about is what other possible distances there are. But let me come back to the thing I forgot and talk about division in R, right? So the problem with division is here. Maybe I will do it here.
Anyway, just go this
Yeah.
way, then that way.
I think I'm
Left to right, then down, left to right again.
so let's. So the problem with defining division on just sequences was that the sequences can have 0. And the sequence might itself not be 0, but it will have 0 inside it. So, if I want to do pointwise division, that does not work. But here, so in real numbers, I do not have just one sequence. I have a bunch of them, and so what I can say is if S is not equal to 0. So, by this I mean a sequence whose limit is not 0, because that is how real numbers are defined. S, so let me write is, so S, so which is the sequence S1, S2, Sn, so on, which is not equal to 0, by which I just mean the limit of the sequence is not 0, because that is what I care about. Then, because of the existence of limit, then there is an n such that if small n is bigger than n, then Sn is not equal to 0. So, this is not true for general sequences. I can have zeros which are far apart, but for Cauchy sequences the elements cannot go too far from each other. So, if my sequence is not 0, then at some point the elements will stop being 0. And so, I can just consider, so S or the not equal to 0, sorry, the zeros end because the sequence is not 0. So, if I have, so I can start another sequence Sn plus 1, Sn plus 2, S capital N plus small n. So, I have this sequence, and this sequence represents the same real number as this sequence, which might have zeros. This one has no zeros, and now I can divide. So, I get the field, and this division is nice. Okay. So, I get the field. So, now let me come back to the question of trying to play with this construction. So, the most obvious element to play with is the distance, and what I want this construction to go through, right, at some point. So, what do I need from a distance? Well, let me not talk about the distance because it involves two arguments. Let me talk about something simpler, which is the absolute value. So, what do I want from the absolute value? So, a function q to q is called, I should just write here, there is not enough. So, so norm or absolute value a function so let me just represent it as absolute value, but with an asterisk to denote that we are talking about some general thing and not the one that geometers mean, is called an so maybe a function. So, this is a function from rationals to rationals is called if 1 I want its result to be bigger than 0. So, that the way I was talking about limits being very close to 0 makes sense. So, 0 and the way I was identifying my sequence was by comparing the absolute values, some absolute values getting very, very close to 0. And so, what I want is the only thing that has absolute value 0 is 0 itself, and x is equal to 0 means the absolute value of x is equal to 0 means x is equal to 0. 2, to get that Cauchy, the product, the sum of two Cauchy sequences is a Cauchy sequence, I need that property that a plus b. So, x plus y, absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. And this is something that you expect from general distances, but here we want them to play nicely with the field structure we have. So, there will be an additional thing which again we need it for the multiplication, which is that absolute value of x y is equal to absolute value of x times absolute value of y. And this means in particular that absolute value of 1, maybe I should put star here, absolute value of 1 is always 1. So, this comes from this fact that it absolute value plays very nicely with multiplication. And so, I want my function. So, if my function has these properties, then the construction I have done will go through with the distance function, which is just, let me say, d star x y is just absolute value of x minus y star. So, the question is, can I have other absolute values on rational numbers? And there is a theorem which is I think called Ostrowski theorem or Ostrowski theorem. I don't exactly remember the name, which says that the ones I am going to describe, the p-adic numbers, are the only other ones. But that depends on some details that we are not covering, which is basically that this absolute value or distance gives me a topology on the space. So, I am not just talking about, here we are just trying to describe algebraic structures like groups, rings, fields, but when they get big enough we need to care about the topology here. And this theorem, what this theorem says is that if we try to do a completion with respect to any absolute value, you will topologically what you will get is the space which either corresponds to the Euclidean one or one of the ones I am going to describe now. So, these p-adic numbers. Okay, but this is like, I do not know, topology we will not touch for now, but it is there just because we have a norm. So, it is already there implicitly, but we will not try to make it.
Well, if you are defining a norm,
Yeah.
distance, the
Yeah.
topology is defined in terms of the distance. So, you have essentially.
You can define topology in terms of distance, but
I suppose this is what the topology you are using.
Yeah.
Defining the distance.
So
you can talk everything in terms of the distance. You don't have to.
No, but they right, like not all topologies are normed.
That's not what I'm saying. I'm saying if you are going through
yeah.
the distance.
Yeah. Yes. Yeah, that's true.
Don't need to talk about topology.
Yeah, this is yes. Yeah. So, we are going through. Yeah, in this case we can only put, we are only talking about norm topologies. But I think the statement itself is about just like is about yes.
But when you say norm topology, do you just mean that there is a metric?
Yes, and there is a notion of open sets which comes from the open walls of that metric. Yeah. Yeah.
Is this absolute value function is a metric?
Yes. No, the absolute value function is not. This thing is a metric. So, which is defined in terms of the absolute value. Okay. Yeah. So, and okay. Yeah. So what? Yes, I think yeah, you are correct that if what the theorem says is this, that So, since we are going through a matrix, we have to have a norm topology, but this norm as a topological space, this topology will be same as one of these. Okay. So, let us come to what these are, and they are not something that we are very used to. So let me and beyond what I have written about finite groups, I actually don't really have a very good motivation for doing things the way we do, except that it works and it's useful for a lot of things. So even though it's not something that's super intuitive for me, it is very, very interesting. And once we have the intuition, we can no, once we have worked with them a little bit, maybe we will get intuition too. Okay, so the first thing I want to define is something called p-adic valuation. And to define it, we have to remember something that number theorists told us to care about, but the geometer was not very interested in, which is prime factorization. So integers, so if n is an integer, then I can write n as product over primes, there is a sign, and then p to the power some power. And if I actually want this to be integer, I want most of these alpha p to be 0. So alpha p are natural numbers with most of alpha p. Let me be
Finitely many non-zeros.
with only finitely many alpha p non-zero. So maybe, which is a perverse way of writing, I should just index my finite set, but it is, let's stick with it, and s is in a sign, so it's plus minus 1. And this factorization is unique, and this unique factorization is a quite general algebraic fact in a certain type of rings. And those are the rings. So let me say what those are. No, do I want to come here? I think so.
Just do whatever you like, because you are anyway messing up all of something, but do whatever you like.
Yeah.
No, okay, next time we will talk. You just go this way, move them up, then go
Where
this way,
was I
move
last
them up.
time?
But anyway, just do it, just do it.
So okay. So I have this prime factorization, and so in the beginning we had this construction which went from Z to rational numbers, and this will be kind of important for us again now. And this construction works, and so this construction had a relation which says that P over Q is equal to R over S, means that P times S is Q times R. And this relation works nicely only, so this works nicely only if works nicely, not here, works nicely because for integers P times S is equal to 0 means p is equal to 0 or s is equal to 0. So, if this is not true, and this is not true for rings in general, that this property holds, the construction we had to go from Z to Q will not work. So, a ring, so this thing, so such a number, so a pair of numbers such p times s such that p and s are not 0, but their product are 0, are called 0 divisors. So, let me write that here. So, 0 divisor So, as a p such that, so p not equal to 0 such that there is an s with and s not 0 with p s is equal to 0. So, if there are no 0 divisors, your ring has a structure which is very, very close to that of an integer, that of integers. So, an integral domain is a ring with no 0 divisors. And the name just comes from the fact that it tries to model very, very closely the properties of integers. And this unique factorization modulo some slight change is a general fact about integral domains. And the slight change is that so integers are very special in that they are exactly two elements which have multiplicative inverses. So, which are +1 and -1. In general, there can't be more. So, you have to allow for multiplication by these inverses, but otherwise factorization is unique. And so, we have, so if you have an integral domain here, so if you have if k is an integral domain, I can do the same thing I did with my integers. So, pair of elements of k with this relation, I can form the field of fractions. So, this rational numbers is just the field of fractions of integers, and the reason I am talking about it here is because fields generally have no nice factorization to talk of, because everything is invertible. But if I can obtain my field in this way as the field of factorization of some integral domain, I can still talk about the factorization of these p and q in this integral domain k, right. Like, so, in real numbers, there is no sense in talking about factorization of a number, because I have not obtained it in this way. But for q, I can still talk sensibly about factorization, but I have to remember I am not talking about factorization here, I am talking about factorization here. So, where should I go now?
Yeah, move it up.
Okay.
You can go from left now, because this is irrelevant. Yeah,
Where?
from the left. Yeah, here.
Okay. So, okay. And yeah. So, if I have an integer, so if I have f r is a rational number, q, then I can also kind of factorize rational number in terms of integers. So, I can write it as, so r is, again there is a sign which is plus and minus, there is a product over primes, and I have p to the alpha p. And the difference from the case before is that now I can allow these alpha p to be negative. So, with s in plus minus 1 and alpha p integers and only finitely many, alpha p are non-zero. So, a corollary of this fact is, so if I fix a prime, if I fix a prime p, I can write r is equal to p to the alpha p times some other r tilde, and this r tilde has no factors of p, right. So, this I have just multiplied all the other prime factors with r tilde co-prime to p. And what do I mean by co-prime? So, this r tilde has some denominator, some numerator, and neither the denominator nor the numerator has a factor of p. So, they are integers. So, and this p-adic valuation that I want to define goes like V p. So, it's basically tells me how many factors of p this number has. So, V p of r is just alpha p. So, if I had to write it directly, I can just say, so once I have this definition, I can say that I can write r as p times V p of r and then r tilde. So, the maximum number of factors, or kind of the only number of factors I can pull out, so that the rest has no factors of p, is this V p. And we will define the distance using this p-adic valuation. But before that, I need to extend it slightly, in the sense, so this right now this is an integer. What I will say is this. So, I will extend it. So, something I should have said, I of course want this r to be non-zero. If r is 0, there is no factorization. So, but I want to extend it, I want to extend this valuation to include 0, and I will do it in a way that I would not have liked if one of my Cal students did it, which is, I will just say that V p of 0 is the symbol, whatever that means. Okay. And okay, so we have this valuation, and we want to know some properties. So, the first one is, I think, which is pretty easy, is that V p of 1 is 0. 1 has no factors of p. V p of r times s is the valuation of r plus valuation of s, and this is kind of the thing that will give us the nice, when we define the p-adic absolute value, this is the one that will give us multiplicativity.
Is this S is the same as here?
As V?
No, this is just some number.
No. So, this is just some rational number. So, r and s are two rational numbers. That is some sign. So, here s is just a sign, and so this, and then what is a bit more annoying maybe is that if I have sum of two, if I have sum of two rational numbers, then there is an inequality which relates their valuations, and here it is minimum of Vp. So, valuation of R and valuation of S. And so, this inequality is saturated if the valuation of P of R, the valuation of R is not same as valuation of S. So, in this case, so what happens is, so they have different factors. So let me just try to work out why that is the case. So, I can have R and S, and I will just assume without loss of generality that this is the one that has, so R is the one that has minimum valuation. So, in that case I can write down, so let us suppose R is P to the P of R tilde, and S is S, yes, here, okay, S tilde. And since this one is the smaller, what I can do is I can write down, so R plus S is P to the Vp of R, and now I will get, here I will get R tilde, and then here I can write down P Vp of S minus Vp of R. So, this number is positive, or at most like at least 0, and times S tilde, right. So, I have this, and I can now try to figure out what kind of factors of P this can have. So, what I know is R tilde has no factors of P, and if these two are not equal, this has a factor of P. So, the total thing can't have a factor of P. So, this is why it can have, so this is why this if they are not same, this inequality is saturated. If they are the same, on the other hand, then this factor is 1, and R plus S might have some factor of P, and in that case I will get a bigger valuation. So, this is going in the opposite direction, kind of as we expect from norm. So, but this is fine, this is not a norm. So, the next thing we want should go there, right.
You go back and then start pulling down.
So, now I can define the p-adic absolute value So, this is just, so I will write as x with the p here to remind me that this depends on this prime somehow, and it is just p to the minus valuation of x. And this p is not so important, it can be any integer, let us say positive integer, but since we already have one available, let us use it. But we do want to exponentiate it, because exponentiation will turn this addition into multiplication. And since, and because of this, what we can say, so we can check properties very easily, the only thing that has valuation infinity is 0, and that means that absolute value of x p is equal to 0 means x is equal to 0. This thing means that not p is, and So, I have multiplicativity, and then this thing means that this thing, so this thing, this will means that x plus y p is less than or equal to p plus y p. And this comes from the fact that this thing, so I know this thing is bigger than the valuation of one of them. So, I am just basically ignoring the other. So, this is true. So, I have these properties. So, I have a good absolute value, and so this gives me some good notion of distance, but this distance is pretty far from what we expect usually, right. So, one thing so let us try to get some intuition for it. So, the easiest thing to do is to यहाँ से इसकी वजह से. So, I will use I will put this thing in the exponential, and so because this is minimum of 2, I can write this as kind of the sum V p plus V s. So, I am missing one term from this sum. Should I try to do this? And so, you can kind of like, because of this, in most of the cases it will basically be the min of one of these. Okay. So, I have a good mit. So, let me try to write down some examples, right, of this distance. So, one thing I want to do is what is the distance from 0, right. So, distance from 0 is just the absolute value of so d is just the absolute value of x, and I can pick up some values which are easy to compute. So, the first one is p. So, absolute value of p is 1 over p, because the valuation is 1. Absolute value of p square is 1 over p square, and absolute value of, and I can say absolute value of p n is 1 over p n. So, as the number is getting bigger and bigger, as this number is getting bigger and bigger, its distance from 0 is decreasing. So, not something we are used to. On the other hand, if I have r prime, let us say q r prime not equal to p, then the absolute value of q to the n is just 1, right. So, it has no power of p. So, all of these are at the same distance from 0. So, in this sense kind of, so normally the circle is all the points which are at the same distance from 0. So, let us say the circle centered around 0. So, all of these points, and there are lots, so I can pick any prime, I can pick any number which is co-prime to p, and its distance from 0 is 1. So, it is on the unit circle with this way of measuring distance, and this is very different from rational numbers, right. They are the only numbers which are at distance 1 are plus and minus 1. So, this has somehow a big circle, big, but it has a circle which has infinitely many points. So, we have this metric. How much time do we have? Okay. Okay. So, we have this metric, and now we can do the same thing we did with the normal absolute value to get some new numbers. So, some new field, and it is called field of p. So, that field is called p-adic numbers. Where should I be here?
Yeah, put it down.
Okay. So, QP, so which is called field of p-adic numbers, is the metric completion. Let me just say completion, because before I just called it completion. So, let us say completion of Q with respect to p-adic absolute value. And so, one thing we would like to get an idea is, so what are the Cauchy sequences here, right. So, and I think the easiest way to do is to remember the base 10 expansion here, right. So, base 10 expansion in real numbers. So, kind of reminder, so base 10 expansion so what does it correspond to in terms of Cauchy sequences? So, what I have is I have some power 10, let us say I start at some big power 10 to the r, then there is a number a which is between 0 to 9. Then the next term there is, let me call it a0, a1, 10 to the r minus 1, a2, 10 to the r minus 2, and I can continue this sequence. So, ak, 10 to the r minus k. This is not a Cauchy sequence, but I can there is a very easy way to get a Cauchy sequence from this, and that is by taking the partial sums, or maybe it itself is also no. So, yeah, this is not a Cauchy sequence, but I can take the partial sums. So, I have a Cauchy sequence whose first term is a0, 10 to the r, then a0, 10 to the r plus a1, 10 to the r minus 1. The next one, which is the last one I will write, is a0, 10 to the r plus a1, 10 to the r minus 1 plus a2, 10 to the r minus 2, and then there are other terms which are written in the obvious way, right. And when we write a number in the decimal notation, it is basically a0, a1, a2. At some point we reach the power 0, then we put a point, and the ones after correspond to the coefficients of negative powers, right. So, this is and the reason this work is that once I start dividing by 10, the distance between 0 starts going less. So, 10 to the r is further away from 0 than 10 to the r minus 1, which is further away from 0 than 10 to the r minus 2, and so on. So, here the way to go away from the way to come closer and closer to 0 in p-adic norm is to make powers of p bigger and bigger. So, we have kind of a base. So, in p-adic numbers, we have kind of like quote unquote base 1 over p expansion. So, what I mean by this, I can have an analog of this sequence, which is, let us say, a0, and then I have p minus r. So, to get, and this a0 is from between 0 and p minus 1. The next one, I want something which has a smaller distance. So, I must increase the power of p. So, there will be a 1 p to the minus r plus 1 and a 2 p to the minus r plus 2, so on. So, this is not a Cauchy sequence, but I can take the partial sums and they will form a Cauchy sequence. Just because the distance, as I increase the power of p, the distance between 0 and the number starts going down. So, and to just kind of illustrate this point, where should I be?
Now you go back and start pulling down.
So there is kind of, so p-adic numbers are series in base 1 over p in this sense. If you remember, like this expansion in base 10, here the base 10 was not special, right. So, it was not special because if I pick another integer, same thing happens. If I decrease the power, if I raise it to smaller power or a negative power, it gets the distance between 0 and this number gets smaller. But here this p is very, very important, because as we saw, if the number does not involve p, the distance from 0 is 1. So, this p is important. So, kind of to get some intuition.
So if you want to represent, so you're starting with the field of rationals.
Yes.
And you're trying to complete it.
Yes.
So that means the rationals should have the usual meaning of a rational.
Yeah.
So if I want to write a Cauchy sequence representing a rational, what would I need to do? It would be, so you take its expansion. How would the expansion look like in that case?
So,
Can you do an example?
I mean, it will look, so let me do an example, but in a slightly different direction, right. Okay. So, let's kind of look at, so what you're probably worried is some kind of convergence, right. So, let's look at some.
Not even convergence, I want to have some intuition about the representation.
Yes, okay. So, but I think this maybe will give. So, let's look at geometric series.
Because like for
in QP, so which I think is quite, in some sense, I think illustrative. So, we have, what I want to do is I have some x, and what I want to do is to compute 1 plus x square plus x cube plus so on, right. So, this so let us say s of x, and this we do in, I do not know when, I think FSC, is that s of x is 1 over 1 minus x if absolute value of x is less than 1, right. So, this is, we are happy with this fact, and the only thing is now we have p-adic absolute value. So, this series in p-adic numbers will converge if absolute value of x in p-adic in p-adic metric, in p-adic absolute value is less than 1. Okay. So, what does that mean? So, the simplest case examples of, so the easiest thing I can write down with absolute value which is less than 1 is p, right. So, p has absolute value 1 over p, and so this series converges, and s of p is 1 over 1 minus p. So, and this is, so if you can, so p is greater than 1, this is a negative number, right. So, but here, so 1 plus p square, they are all positive. So, this is another way. So, this is again saying that this p-adic absolute value does not play too well with the ordering. Like we are used to a relation between ordering and distance. Here this does not work, right? So somehow in the normal topology, बच्चे अगर आप लंबे हैं, you are to the ये side left, but this is not here true here.
So you're kind of sacrificing ordering and keeping the distance.
Yeah, so so this distance, the relationship between distance and ordering is not as nice. So it has both ordering and the distance, but they just do not play as nicely with each other as.
It's not inverted.
What's inverted?
Like the bigger the P is.
Not always, right? It's only because it's only happening because many I have taken the power of p. If it was not the power of p, this inversion wouldn't happen. So this is 1 over p. Similarly, I can take any other power of p, same work. I can also take this x to be, let's say, if x is alpha p, where alpha is co-prime to p, the series also converges and
All those x's where p is a factor.
yeah, with a positive power.
With positive power.
If it's negative power, it will not converge, right? And which is exactly the opposite. If I take the rational, if I take the normal metric, if it was p with a negative power, it will converge, and otherwise it won't. But on the other hand, if I take if I take this x to be some q which is not co-prime to p, it will not converge whether I take negative powers, positive powers, doesn't matter, right? Okay. So so this.
So I now realize. So for the rational is nothing special.
Yeah.
It's just the you're just insisting I'm going to do representation.
Yeah.
It's 1 over p. But
Yes.
it's rational.
Yeah, they're just rational. So rational basically means, so this sequence, so two things can happen, and this is again the same thing that happen when you do when you want to know when you know the relationship between the decimal expansion and the rational, like p over q representation. So if this sequence eventually becomes 0, you will get a rational number. But that's not the most general case. It can also become periodic after a certain point, and you will still get a rational number. But otherwise, so generally, so let me say that here. So should
Pull it up and this way.
so generally, a p-adic number can be represented as a series, and the series will look like this. So what should I call it? Maybe kept n is, so there is a minimum power of p, and this minimum power of p takes the place of the maximum power of p. So 10 to the 10 p to the minus r, and then there is a0, so plus a1, and I increase the power of p because I want to get closer to 0, and a2 p to the minus r plus 2 plus so on, and ak p to the minus r plus k plus so on, and this series can continue. And each of these terms has smaller norm than the one before it.
So what's multiplying it, that doesn't affect the norm.
So yes. So but if again, if it's co-prime, so ak are in 0 to p minus 1.
Yeah, so they're co-prime.
Yeah, so they're co-primes. And so, this is generally how we can represent a p-adic number, and this maybe this is the time to stop, because the next thing I wanted to do was
This was the last question. I guess because of the properties which you, of the distance, it could still happen that when you make these partial sums, it's still Cauchy.
yeah.
In the sense that the norm is, if you take, so what I'm trying to say is, if you take two sequences and you are saying that they represent the same rational number.
Yeah.
So like previously we said that if you have okay, I'm confused.
Yeah, what will happen that the norm property is saying that the norm of sum is less than or equal to the norm.
Yeah, yeah. So that's what my intuition was. Yeah.
That will be invoked there in the.
This is what I was trying to say. When you take the differences,
Yeah.
you want it to be Cauchy, so you want those things to be going to zero.
Yes. So
Yeah, that's what I meant.
So for example, this thing has norm which is p to the r.
Yeah.
If you remove the first term, the norm will be p to the r minus 1. If you remove this, the norm will be p to the r minus 2. So it's decreasing.
So in partial sum, the previous sums will
Yeah.
go away.
So this is so this thing will work. Maybe like one thing I can introduce, but continued last time is this thing called ZP. So what we saw with real numbers is that, so we have this construction which takes us from integers to rational numbers, but there is no such kind of, there is no analog of z for r. So I cannot write down, so I cannot write real numbers as ratios of p over q of some other set, unless the set is r itself. That is fine, but that does not give me anything new. So it does not make the set I am starting with smaller, but this is not the case with qp. So there is a set, so zp, and it is very easy. So in this case what happens is this valuation takes values in integers, except for that infinity business, it takes values in integers. So what I can do is I can separate out the part in which the valuation is positive. So I can define it as subset of x in qp and vp of x is greater than equal to 0. And you can check, so this set is closed under addition multiplication, but here, so if and since it is pretty easy to check. So if x if vp of x is r, then vp of x inverse is minus r. So if unless, so there is a special case where this valuation is 0. In that case, both the number and its inverse will be in this set, but if the valuation is non-zero, only exactly one of the number or its inverse will be in this set. So this is in some sense a smaller set, and it is not a field, but what it is an integral domain. You cannot see, so and here I can see that I get this if my series starts, this r is negative or 0. So what I have, so here, so what this gives me is a set such that if I do the process of taking fractions in this set, I will get qp. I will get the p-adic numbers, and this set is nice because this, in some sense, it allows me to do reduction modulo p. So in p, so here I cannot always do reduction modulo p because of this negative power business.
So this is not the set of the usual integers.
No.
You're saying that if you do the q over p business here,
Yeah.
you still get the qp, the full.
Yeah. Yes, I get the full. I get the p-adic numbers.
P-adic numbers.
Yes. So this is a subset of p-adic numbers. So this is bigger than. So this is a subset of p-adic numbers with positive valuation, 0 or positive valuation.
What is QP?
So, QP is the set of p-adic numbers. So, the completion of Q with p-adic. Yes. So, this is a subset of the completion, and I can start with this set, do the P over Q business and get QP.
So without doing the completion?
Without doing the, so this set will be complete already with QP metric. But you can also, so this is what we will do next time. So you can also start from the rationals, but instead of starting, you can start with rationals. Instead of adding inverses of everything, add inverses of everything except P and complete those, and then you will get this. So this is, you don't try to add inverse of P in that.
Okay, let's do it.
Yeah.
Okay, thank you very much.
When you say completion, do you mean in the sense of it's a complete metric space?
Yes. With the metric being the that's the definition of complete metric space, right? It's the equivalence classes of Cauchy sequences, such that to identify Cauchy sequences which have the same value.
So prime will always have the unit length.
Prime, the one prime will have the unit length, and that's the one that appears in QP. Oh no, sorry, no, that will have
All
one
the
over
primes.
P. All the other primes
which are not equals to P.
P.
Or co-prime numbers which are not equals to P.
The length of P is 1 over P.
In the middle, there was a point where you constructed Q attached with square root of 2 square root of minus 1.
Yeah. 2?
This is everything that
You extended Q with square root 2 and square root of minus 1.
Yes.
If I'm not wrong, shouldn't there be 4 rational parameters for that?
What do you mean for
A, B, C, and D.
Yeah.
Oh yeah, it's, square root of minus,
Square root of minus 2.
There should be square root of minus 2, yes.
Yes.
No, but can you get it in? Yeah, they should be. As a vector space, it should have
Dimension.
a dimension 4, yes.
Okay, thank you. Okay.